हेलो एवरीवन, माय नेम इज करण मशरू। वेलकम टू दिस वीडियो। और इस वीडियो में हम देखने वाले हैं गीक्स फॉर गीक्स जॉब-A-Thon कोडिंग कंटेस्ट में पूछे गए क्वेश्चंस के सॉल्यूशंस। सो फर्स्ट ऑफ ऑल लेट अस स्टार्ट विद द फर्स्ट क्वेश्चन, दैट इज फाइंड बिट्स। सो व्हाट डज द क्वेश्चन से? यू आर गिवन टू पॉजिटिव नंबर्स and an x. Your task is to find out the number of I such that I is between 0 and 2 की power n minus 1 and have bitwise end with x equal to x itself, given that x lies from 1 to 2 की power n. Formally, find out the number of I such that I and x is equal to x, given that I and x both lie between 1 and 2 की power n. So basically what they are trying to say is, if I have been given two integers, let's say this is the first question, find bits. So let's say I have been given two integers and an x. So I need to find the number of numbers I such that I and x is equals to x. Okay, and I and x both lie between 1 and 2 की power n minus 1. So there is no equal to sign here, so I can also write this as like this: 1 x comma I less than equal to 2 की power n minus 1. Okay, so given in the input n and x, what are the number of values of I such that I and x is equal to x? Now you see here, if I want I and x is equals to x, since this is an AND operation, if in the result I want x, it means all the bits which are set in x must be set in I as well as x, right? So basically if I write a and b is equals to c, so all the bits which are set in c are set in b as well as a. That is the definition of AND operation. All the bits which are set in both will be set in the output when you take bitwise AND between them. Now, if the output is x, then all the bits which are set in x must be set in x as well as I. Now, all the bits which are set in x are obviously set in x. So basically, I need to find the number of values of I in which the bits which are set in x are set in I. Other bits can be set, cannot be set. Okay, so basically you need to find the number of values of I such that I has all the bits set. Set means bit value is 1 when represented in binary format, has all the bits set which are set in x. So those bits which are set in x must be set in I. Other bits can be set, cannot be set. Okay, for example, if I take n is equals to 4 and x is equals to 3, so if n is equals to 4, first of all, what is the range of my I and x? It is less than 2 की power 4. So can I say all the 4 bit combinations? Because what is the largest number? Largest number is 15, which is 1 1 1 1. Smallest number is 1. 1 can be written as 0 0 0 1. So if my n is 4, I am considering all the 4 bits combinations. If the n is 5, I am considering all the 5 bits combinations, right? So my I will be a 4 bit combination. Okay, now x is 3. So what I said, I should be such that the bits which are set in x must be set in I. Other bits can be set or cannot be set. So x is 3, right? So 3 can be written like this. So at least these two bits must be set in I. Only then when I do I and x, my output will be x, right? Now this bit can take any values, so it can take either 0 or 1, and this bit can also take any value, either 0 or 1. But this bit is fixed, it should be 1, and this bit is also can take only one value, that is 1. So total possible values of I are 2 into 2 into 1 into 1, that is 4 possible values. Okay, so 4 possible values will be 0 0 1 1, 0 1 1 1, 1 0 1 1 and 1 1 1 1. This is 15, this is 3, this is 7, and this is how much? 3 and 1 2 4 8. This is 11. So for any of the numbers, when you take bitwise AND of any of this number with 3, you will get 3, right? Because here both the bits of 3 are set, right? So when you do bitwise AND with 3, you will get 3. So the basic idea is, if the number is of if whatever be the value of n, that would be the number of bits using which we will represent I. Out of it, some of the bits which are set in x must also be set in I. Other bits can be set, cannot be set. Okay, so if I have been given n, so the all my I values will have n bits, right? Can be represented as n bits. They can have leading zeros as well. And if I have been given x, and if there are, let's say, set number of bits in x, then there will be n minus set number of bits in I, where I can keep 0 as well as 1. For example, here the total number of bits to represent the number is 4, and in x, that is 3, 2 bits are set, right? In x, 2 bits are set, so other two positions can take any value. So total number of bits minus number of set bits in x, these are the number of bits which can take either 1 or 0. So the total number of values of I will be 2 ki power n minus set, where set is the number of set bit in x and n is the given in the input. Okay, where my I will lie between 1 and 2 ki power n. Right, now let's look at its code. So let me take it from here. Okay, so first of all, I have taken answer as 0. Then I have taken set equal to 0, in which I will store the number of set bits in x. So while x is greater than 0, if x mod 2 is 1, if it is an odd number, then the last bit will be set. So I'll do set plus plus and divide x by 2. So this while loop will count the number of set bits, okay, in x. I hope you understand it. For example, if the x value is 1 1 0 1 0, so how many set bits are there? 3. How can you know? If the number is odd, then this bit will be 1, otherwise it will be 0. Now this number is even, so this bit is 0, so I'll not change my counter. Okay, my set will remain 0 only, and I'll divide this number by 2. So it will become 1101. Now this bit came at 1's position. This number is odd, so this bit is 1. So I'll make my set counter as 1. I'll again divide this number by 2. So 110. This bit is 0, so number is odd, so set will remain 1 only. Again divided by 2. So this bit is 1, so the number is odd, so my set will become 2. Again divided by 2. So now this number is odd, so this bit is also set. So again increment the counter, it will become 3. Again divided by 2, it will become 0. I'll come out of the while loop. So the number of set bit is 3. Okay. So this will give you the count of set bits, and total number of bits to represent I is n. So those bits which are set in x must be set in I, and for the remaining n minus set bits you have two choices. So total number of possible answer is 2 ki power n minus set, and then you can return this answer. Okay, now let's move on to the next question. So now let's go through the second question, that is prime inversions. What does question say? Given an array and its size n, which consists of positive integers. So we are given an array ARR and the number of elements in it is n, and it contains positive integers. Find the number of inversions in the array B. So in array B we need to find the number of inversions. Now what is array B? Where Bi is the number of distinct prime divisors of array of I. So how do you get B of I? So for example, if array of I is 9, so how many distinct prime divisors are there of 9? 1. Only 3, because 9 is 3 square, right? There is only one distinct prime divisor. So B of I, where array of I is 9, B of I will be 1. If array of I is 15, so B of I will be 2, because 15 has two distinct prime divisors, 3 into 5. So in that way you generate the array B, and in array B you need to count the number of inversions. Two array elements, array of I and array of j, form an inversion if array of I is greater than array of j and I is less than j. So what is an inversion? If you have two indexes I and j, where j is greater than I, but array of I is greater than array of j, then that's called an inversion. Okay, so we need to tell the number of inversions in array B. So let's first take the first example and understand the question better, then we'll move on to the solution. So the first example is 10 3 1 2 and number of elements is 4. Okay, so you have number of elements as 4 and array is 10 3 1 2. Now first of all you need to find array B. So what is array B? B of I is nothing but the number of distinct prime divisors of array of I. So 10 can be represented as 2 into 5. So there are two distinct prime divisors. So this will be 2. 3 can be represented as 3 ki power 1. There is only one distinct prime divisor. 1 have no prime divisors. 1 is not a prime number. So there are no prime divisors. So this will be 0. And 2 has one prime divisor, 2 itself. So this will be 1. So this is your array B. Okay. For example, if let's say your array B was 225. So 225 can be represented as 5 into, so what will be it become? 5 into 45, right? Sorry, 5 into 5 fours are 20 and 5, okay, 5 into 45. So this can be represented as 5 into 5 into 3 into 3. So this is nothing but 3 square into 5 square. So there are two distinct prime divisors, 3 and 5. So if array of I is 225, B of I will be 2. Okay, so in that way you form array B. Now in array B you count the number of inversions. So what is an inversion? In the array, if I have two indexes I and j where I is less than j, and if array of I is greater than array of j, so I index is smaller than j but the value at I index is greater than j. For example, I index is 3 and j index is 7 but the value here is 15 and the value here is 9. So this is known as one inversion pair. So I need to tell the number of inversion pairs, okay, in array B. So if I take this example, my array B is 2101. Okay, so here this is one pair, 2 and 1, this is another pair, 2 and 0, this is third pair, 2 and 1. Okay, so 2 1, 2 0 and 2 1, these are the three pairs. Then this 1 and 0 also forms an inversion pair, 1 and 0. Then there are no other inversion pairs. So total number of inversion pairs is 4. That is what is asked in the question. Now how do you solve this question? So I'll divide the solution into two parts. First is generating array B. How do you generate the array B? Generating array B. And another is counting inversions in array B. Counting inversions in array B. Okay. So let's first tackle the second part, counting the number of inversions in array B. So see, the brute force method to count the number of inversions in array B is what? Consider all pairs. So use two loops, right? Use two loops and generate all the pairs I comma j where I is less than j, and if array of I is greater than array of j, then do counter plus plus. But this will go in n square time and this is inefficient. So I need to find some efficient way. So for this I will use merge sort. Okay, I will use merge sort. Now I am not going to cover the whole merge sort theory in this video. Okay, so because then that will become a separate topic. So you should know the implementation of merge sort. Okay, so I'll give you a rough idea. So what do we basically do in merge sort is, let's say this is my array. Let's say there are 8 elements. Okay, let's say it is 3 1 2 9 3 1 4 7. Okay, so first of all we keep dividing the array into two parts until there is only one element left. Okay, this is the merge sort algorithm. So it will become 3 1 2 9 and the right hand side part will become 3 1 4 7. Then again divide this into two parts. So this will become 3 1 and divide this into two parts. This will become 2 9. Divide this into two parts. This will become 3 1 and divide this into two parts. This will become 4 7. Again divide it into two parts. 3 1 2 9 3 1 4 and 7. Now once divided, we backtrack and combine. What we do is we try to sort these smaller sub arrays. So we try to sort this part and so on. Okay, and we during backtracking we sort the smaller parts and at the end we get the whole array sorted. So we start from here. Now single element is sorted in itself. This is also sorted in itself. So all the single elements are sorted. Now I want to combine this 3 and 1 to get a sorted array here. So what I will get here? I will get 1 and 3. I will combine 2 and 9, and the sorted order I will get is 2 and 9. I will combine 3 and 1, and I will get here 1 and 3. I will combine 4 and 7, and I will get 4 and 7. Now I will combine this 1 3 and 2 9 to get this part sorted. Okay, so this will become 1 2 3 9, and this part will become 1 3 4 7. Now I'll combine this sorted order and this sorted order to get the full array sorted. So I'll get 1 1 2 3 3 4 7 and 9. So this is my sorted array. Okay, now how do we combine two sorted arrays? For example, at this step I had this left part sorted and right part sorted. So how can I combine and get this full part sorted? So let's take that example, because that is important. That is how that is where I'll count the number of inversions. Okay, so I have 1 2 3 9 and 1 3 4 7. Okay, so at a certain point of time I will have 1 2 3 9, and here I will have 1 3 4 7. Now I want to combine them and form the sorted array. Okay, now understand one thing. In the sorted array, the smallest element will be the smallest element of this part or this part. The smallest element of the whole array will be smallest element of this part and this part, right? So if I combine the smallest element of this array and smallest element of this array and pick the smaller out of those two elements and place it here, that would be correct, right? So what I will do is I will keep one pointer I here, I will keep one pointer j here, and compare both of them. Okay, and whenever they are equal, I'll pick from the first part. So 1 and 1 are equal, so I'll pick this element and add it here, and then move my I index here. Now the smallest element remaining from this part is 2, and the smallest element remaining from this part is 1. So I'll take 1, and because between 2 and 1 the smaller is 1, so I'll take 1 and then move my index j here. Now between I and j index, so I index represents what? The smallest element from left part which is yet to be taken in the answer. J represents the smallest element, index of the smallest element on the right part, which is yet to be taken in the answer array, in the sorted form. So now 2 and 3, which is smaller? 2, so I'll take 2 and increment I. Now 3 and 3, both are equal, so I'll take the left part. So I'll take 3 and increment I. Now 9 and 3, smaller is 3, so I'll take 3 and increment this. 4 and 9, smaller is 4, so I'll take 4 and increment this. 7 and 9, smaller is 7, so I'll take 7 and increment this. Now this is out of bounds, so I'll take 9 and increment I, and I'll get the combined sorted array. Now during this combination of two sorted arrays, when I am combining two sorted smaller arrays and forming a larger sorted array, at that time I will count the number of inversions. How? See, first of all, I have 1 2 3 9. And here I have 1 3 4 7. Now this is my index L, this is my index M, this is my index M plus 1, and this is my index H. Basically this is the lower index, this is the higher index, and this is the mid portion. Basically the same array is we are considered dividing into two parts, right? So but it is the same array, so if this is at M index, this will be at M plus 1 index, right? Now see, suppose my index I was here and j was here, so both of them are equal, so I'll take this one, I'll take 1 and I increment I. Now this 2 and 1, this one is smaller, so whenever while combining these two smaller sorted arrays into a larger sorted array, whenever I pick an element from the right hand side, it means on the right hand side I have a smaller element than on the left hand side. It means it's an inversion pair. So there is an inversion pair between 2 and 1, right? But these smaller arrays are sorted in themselves. So this part is sorted and this part is sorted. So if this 1 is smaller than this 2, then this 1 is also smaller than this 3, and this 1 is also smaller than this 9. So basically 1 is forming inversion with 2, 3 and 9. So whenever I am combining two sorted smaller arrays to form a larger sorted array, and if I pick the jth index element, that is the right hand side index element, then the number of inversions this J index element forms is nothing but m minus I plus 1, because it will form inversion with all the elements from index I to index m, and the number of elements from index I to index m is m minus I plus 1. Okay, so whenever in the merge sort I am combining two smaller parts, and if I am taking an element from the right hand side, at that time in my number of inversions pair counter I'll simply increment m minus I plus 1, because this jth index element is forming inversion pair with all these elements. Okay, now so our this part is done. Okay, I'm not going in too much depth of merge sort because then it will become a separate video, right? So our this part is done. Now how do I generate array B? That's the one part remaining. Okay, so how do I generate array B? So Bi is nothing but a distinct number of prime divisors of array of I, right? So how do I count that? So first of all, if I want to count the number of distinct prime divisors of array of I, so let us understand two things. For example, if I keep a counter variable as 0, and if I want to count the number of prime divisors of array of I, okay, so what I will do is I will say for I equals to 2, I is less than equal to array of I, and I plus plus. If I is a prime number, okay, so if prime of I, let's say I have written a function which returns whether a number is prime or not. If prime of I is true, then I will check if array of I modulo I, sorry, here I have taken I, no, so there is a bit mistake, so let us take this as J, okay, because I am taking here I, so I cannot take this index also as I, right? So if array of J modulo I is 0, then that's a prime divisor, so I will say counter plus plus. Okay, so I traversed from 2 to array of J, and if I is a prime number and if it divides array of J, then that's a distinct prime divisor of J, array of J, so I'll do counter plus plus. Okay, and then I will say B of J is equals to counter, because that is the number of distinct prime divisors of array of J, right? Now there are some things to notice here. How will I calculate whether I is a prime number or not? And second thing is, do I need to go till array of J, right? So let's answer both of them one by one, because I want to make this more efficient. Okay, so first thing, what I will okay, so let's understand this first. So my loop goes from 2 to array of J. Now instead of going till array of J, I can go till square root of array of J. I can go till square root of array of J. Okay, now why so? Because there can be at max one prime divisor of array of J which is greater than square root of array of J. What do I mean by this? So basically I do not need to go till array of J. I'll only go till square root of array of J. Why? So my time complexity will improve. This is big O of array of J. That will be big O of square root of array of J. Now why so? Because for a value array of J, there can be at max one prime divisor which is greater than square root of array of J. There may be none, or there can be at least one. Okay, so there will be 0 or 1 prime divisor which is greater than square root of array of J. There cannot be more than one. There will be either 0 or 1. Why there cannot be more than one? Because let's say this is your number line, this is 1, and this is, let's say, a number P, and here you have square root of P. So square root of P into square root of P is equals to P. Now let's say there are, so let's contradict our assumption that there are more than one prime divisors which are greater than square root of P. So let's say this is one prime divisor P1 and this is one prime divisor P2. So my number P can be represented as P1 into P2 into whatever the remaining terms would be, right? Now P1 and P2 both are greater than square root of P. and square root of p into square root of p is p, and p1, so p1 into p2, this part will be what? This is greater than square root of p, this is greater than square root of p, so the multiplication of both of them would be definitely greater than p, right? For example, if p is 25, so square root of p is 5. If I take two numbers greater than 5, let's say 7 and another is 9, so that is obviously greater than 25, right? So if there are two prime divisors of p which are greater than square root of p, then their product itself will be greater than p. So this whole term cannot be equal to p. So our assumption was wrong. So there can be at max one prime divisor which is greater than square root of p. Okay, for example, if I take the example of 14, so 14 is 2 into 7. Now square root of 14 is how much? 3 point something, 3 point dot dot dot. So there is one prime divisor which is greater than square root of p, but there cannot be more than one prime divisor. So what I can do is, instead of finding prime divisors up till array of j, I can go only till less than equal to square root of array of j. Okay, then what about the prime divisor which is greater than array of j? If it exists, there can be one, but it can be, so I will handle it separately. Okay, I will let you know, I will tell you how. But is this clear? So our loop will run till square root of array of j. Another thing, how do I check whether a number is prime or not? Okay, now what I said, that my loop will go till square root of array of I, right? In the question, it is said that array of I is less than equal to 10 ki power 7. Okay, so my square root of array of I will be less than 10 ki power 4, I can say, because 10 ki power 4 into 10 ki power 4 is 10 ki power 8. So square root of 10 ki power 7 is obviously less than this, right? So I only need to, so my loop here less than equal to square root of array of j will not exceed 10 ki power 4. Okay, now for every element, if I call whether that number is a prime or not, I'll do repetitive work. For example, if a number comes 3876, okay, 3876. Now I check whether this is a prime or not. Again, when it comes, I'll again check. Again, when it comes, I'll again check. So this is also a waste of time. So what I will do is, from 1 to 10 ki power 4, I'll store all the prime numbers. Okay, I'll store which all are the prime numbers from 1 to 10 ki power 4. First of all, okay, I'll do pre-processing of that, so I do not have to calculate it again and again. So how do I do that pre-calculation? So basically, first let me write down the pseudo code, then I'll explain it. It is called sieve of erenthesis. So I'll take one prime array of size 10 ki power 4 plus 1 and initially make all of them as 1. So prime of I is 1 when I is a prime number, and prime of I is 0 if that's not a prime number. Okay, so by default I have made all of them as 1. Okay, now I will say prime of 0 is equals to prime of 1 is equals to 0, because these two are not prime number. Now for I equals to 2, I square I is less than equal to 10 ki power 4 and I plus plus. If prime of I is 1, if prime of I is 1, if I is a prime number, okay, then its multiple cannot be a prime number. So I will say for j equals to I square, j is less than equal to 10 ki power 4 and j plus is equals to I. So I square, then I square plus I square plus 2I, all of this cannot be prime, because if I is a prime and it divides I square, so I square cannot be a prime, I square plus I cannot be a prime. So I'll say prime of j is equals to 0. So in this way you can calculate the all the values whether they are prime or not till 10 ki power 4. Now I am not going into the proof of this right now. Okay, so this is known as sieve of erenthesis. Okay, so you calculated the whether all the numbers are prime or not, right? So now you can directly utilize that, right? So now what I can do is, for a particular element array of I, I'll make a counter value as 0. Okay, Now what I will do is I will say for j equals to 2, because prime number starts from here, j square is less than equal to array of I and j plus plus. So if prime of j is 1, first of all it must be prime. Now I can directly check from this array, right? So every time a number gets repeated, I do not have to calculate whether it's prime or not. I can check whether this index is 1 or 0, this index is 1 or 0, this index is 1 or 0, right? If it is 1, it's a prime, otherwise it's non-prime. So if j is a prime number, then I will check whether array of I is divisible by j or not. So if array of I modulo j is 0, then I will say counter plus plus. So I have got one distinct prime of array of I. But what I will do is I will remove all the occurrences of j in array of I. So for example, if array of I is represented as prime 1 की power r1 into prime 2 की power r2 and so on. So if it is divisible by p1, I'll remove all the r1 occurrences of p1 in array of I. So what I can do, while array of I modulo j is 0, while j can divide array of I, keep dividing it. So I'll say array of I is equals to array of I divided by j. Okay, but I'll do counter plus plus only once, because I need to count number of distinct prime numbers. Okay, so in this way the maximum loop will go till square root of array of I, and for all the numbers which are prime and which divides array of I, I'll do counter plus plus. Okay, now what about if there is a prime divisor which is greater than array of I? So if it exists, we are only going till square root of array of I, right? And we are removing the occurrences of prime divisors which are less than equal to square root of array of I. So ideally, if there is no prime divisor which is greater than square root of array of I, after coming out of this loop, my array of I should become 1. And if it exists, that will be array of I itself. For example, let me explain it to you. For example, if let's say you have 14 and let's say you have 54. Okay, so 54 you start with I equals to 2. Now 54 is divided by 2, so you remove all the occurrences of 2 from it, so it becomes 27. Now your I becomes 3. So 3 is 3 star 3 is greater than less than equal to 27. Yes. So I'll keep dividing it. So this will become what? 9, then 3, and then 1. Because until I can divide, I'll keep dividing it, right? So this will become 1 and I'll come out of the loop. Okay. So the number of distinct prime divisors is 2. So finally, since there was no prime divisor which was greater than square root of array of I, and at every time I encounter a prime divisor, I was dividing that number with that prime divisor. So ultimately that number should become 1, because if the number was initially p1 की power r1, p2 की power r2, p3 की power r3, I have removed all the occurrences of p1, p2 and p3, so it should become 1, right? But if there is a factor, prime factor, which is greater than square root of I, then that will be that number itself. So if 14, so for 14 I will be equal to 2. Now this is a prime divisor, so I'll divide 14 by 2, so it will become 7. Then I'll say I equals to 3. Now 3 star 3 is greater than array of I. This j will become 3 and array of I is 7. So 3 star 3 is not less than equal to 7, so I'll come out of the for loop. When I come out of the for loop, I have array of I greater than 1. It means this is the prime divisor which is greater than square root of array of I, which has not been detected yet. Okay, so after coming out of the loop, if your array of I is greater than 1, it means this itself is a prime divisor which is greater than square root of original value of array of I. So I'll simply do counter plus plus. So in this way, using this for loop and this if condition, I can calculate number of distinct prime divisors of array of I. So finally, I can simply say B of I is nothing but C, where C is the number of distinct prime divisors of array of I. So in this way, I can generate the array B, and then using the modified merge sort, I can count the number of inversions in array B. Now let's look at its code for better understanding. Okay, so let me take the solution from here. Okay, let me make it full screen for better viewing. Okay, so here is where my function starts, prime inversions. I have given n and vector array A. So I have taken one extra array B. So is this the array B which I need to generate? No, this is not that. In merge sort, we need an extra array of size B. This is that. Okay. So how will I generate array B? So I will replace my vector array A only with B. With B means in the question it is given that array B is the number of B of I is number of distinct prime divisors of array of I. So I will store that value here only in vector array, because now after that original value of array is useless, right? I have taken one prime array to store whether prime of I is 1 or 0 depending upon whether the number is prime or not. Then I have taken one answer variable as 0, and I have taken one counter variable. So by default, I have assumed all the numbers to be prime. Then I have set prime of 0 and 1 to be 0. And then I have run a loop from 2 to here I say 10,000. Here I can also use I square. Okay. And if prime of I is 1, then starting from j equal to I square to 10,000, j plus I will make prime of j 0 if prime of I is 1. Okay. So let me give you a dry run of how this sieve of parenthesis works. So it is, let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's say my n value is 12. Okay. And this is 0. So by default, I'll mark all of them as prime, right? Now I'll say 0 and 1 are not prime. Now starting from 2 up till square root of n. So square root of 12 will be what? I'll go till 3, right? And if that number is 1, if it is prime, then for all its multiplications, I'll mark them as 0. So now this 2 is a prime number. So its multiplications starting with 2 square cannot be prime. So 2 square is 4. So this is not prime. 4 plus 2 is 6. This is not prime. This is not prime. This is not prime. And this is not prime, because they are divisible by 2. Now I'll again move further. So this is prime. So 3 square is 9. So 9 cannot be prime. 9 plus 3 is 12. This cannot be prime. And after that, there is no number. And then I'll not go to 4, because 4 square is greater than 12, right? So wherever there is 1 is a prime number, wherever there is 0 is not a prime number. Okay. So I have calculated the prime values here. Then I have run the loop from 0 to n, and I have made counter as 0. For j equals to 2 to square root of array of I, if j is a prime number and if array of I is divided by j, then I'll do counter plus plus and remove all the occurrences of j from array of I. Then if array of I is greater than 1, it means there is one distinct prime divisor greater than square root of I. So I'll do counter plus plus for that. And then I will say array of I as C. So instead of taking a new array B in which I will store the count of distinct prime divisors, I am storing it in array only, because now old value of array is useless. So this is how I have generated that, and then I'll pass it to merge sort, where I have said that merge sort the array from 0 to n minus 1. This is the merge sort to be array to be merge sort. This is the auxiliary array B, and this is my answer variable in which I will store the number of inversions, and finally I will return the number of inversions. Now let's look at the merge sort code. So I'm not going in very detail, but if the number of elements is more than 1, so if L is less than H, divide it into 2 parts. So take M as L plus H by 2, call merge sort on left part, that is L to M, call merge sort on right part, that is M plus 1 to H, and then do the merging of these 2 parts from LMH. Array is the original array, B is the auxiliary array, and your answer variable. So this merge part is written here, where you take I as L, J as M plus 1, and then from I to M is one subarray, from J to M plus 1 to H is another subarray, both are sorted. Now you want to combine and form the larger sorted array. So while K is less than equal to H, if I is within the limits and J is within the limits, then you compare array of I and array of J. Otherwise, if only I is within the limits, j is out of the bounds, then you take b of k as array of I and do k plus plus and I plus plus. So you are storing the sorted array in auxiliary array b. Again, I am not going in very depth. I hope you know the concept of merge sort implementation. If I is out of bounds, I'll take b of k as array of j, and if both of them are within the bounds, I'll compare array of I and array of j. If array of I is less than equal to array of j, then in the sorted array, b of k will be array of I will be taken k plus plus I plus plus. If array of j is less than array of I, then that will be taken and the number of inversions will be m minus I plus 1, which I will add to the answer. And then I'll do k plus plus and j plus plus. Okay. And then you'll again store back the sorted array in the original array ARR for further steps. So this is how you will calculate the number of inversions and finally return it. Now let's submit this code. Okay, so it has been solved successfully. Now let's move on to the last question. So now let's look at the third question, that is range some digits. So first of all, let me explain you what is given in the question. Then we'll go through the question line by line. Then I will dry run on an example. So question will be clear and then we'll move on to the solution. Okay. So basically in range some digits, what is given is you are given an array which contains n positive integers. Okay. And you need to operate q number of queries on it. Okay. Q number of queries. Okay. Each query has 3 digits. So queries is given in the form of a 2D array whose name is queries. And the size of this queries 2D array is q cross 3. So there are q number of rows and 3 number of columns for every query. So each query is of the format 1LR or 2LR. So what does this mean? So query is either of type 1 or type 2. So if at the 0th index of the ith row, at the 0th column, if the value is 1, it is type 1 query. If the value is 2, it is type 2 query. For type 2 query, what you need to do is you need to add sum of elements in array from L to R. Okay, so in the given array from L to R, whatever are the elements, you need to add the sum of elements to a answer list. Okay, so add sum of elements in an array from L to R to a answer array. Okay, and for query of type 1, what you need to do, for all the elements from L to R position, you need to update their values. Okay, so update the values of array of I where I lies between L and R. Okay, now how do you update the values? What is the rule for updating the value? So you update the value to the number of digits in the current value. What do I mean by that? If a value array of I is 1, 2, 3, 4, 5, and if there is a query of type 1 from L to R, and if I index is there in L to R, so you need to update it. So you will update it with the number of digits in the current value. So how many number of digits are there here? So you will update it to 5. If array of I is, let's say, 2, 2, 2, 3, 3, 3 and 4, then you will update it to 7 because there are 7 number of digits. Okay, so you need to, there is an array with n elements, you need to operate q queries on the given array. If the query is of type 1, you update the values as mentioned. If the query is of type 2, then you need to add the sum of elements from L position to R position in an answer array. And finally, you will return an answer array. Return this answer array, which will basically contain sum of elements from L to R for all the queries of type 2. Okay, now let's go through the question line by line. You are given an array, its size n, a positive integer q denoting the number of queries, and matrix of size q cross 3. These are the things given. For ith query, queries of I1 and queries of I2 will represent the start and end index of that particular query respectively. So for ith query, as I said, in the ith row there will be 3 columns. The first column will denote, the 0th index column will denote either the queries of type 1 or type 2, and index 1 and 2 will represent L and R. So basically it will represent a subarray, starting and ending index of a subarray for that query. Okay, and queries of I0 will represent the type of query. Okay, if queries of I0 is 1, it means if it is of type 1, you have to update the values of array of j to the number of digits of array of j for all j between L and R, that is queries of I1 and queries of I2, as I mentioned. If query is of type 2, you have to store the sum of elements that are in the range from queries of I1 to queries of I2 in the range from L to R in an answer array. Okay, so you store the elements, the sum of elements from L to R in an answer array. Finally, return the answer array after processing all the q queries in the given order. Okay, now let's look at this given example and understand. So for first of all, this is the array which you are given and q queries you need to update. Okay, now the first query is of type 1 and you need to update the values from second position to third position. One thing which you need to notice here is that here the values of L and R are given one based indexing. Okay, so when they are saying second to third position or second index to third index, our original array is 0 based index. So if they are saying 2 to third index, actually we have to update 1 to 2 index. Okay, so basically they are talking about this 2 to third position means 1 to 2 index. Okay, so if I update this, so this 1 2 3 4 will become 4 because number of digits is 4, and 5 will become 1 because in 5 number of digits is 1. So after the first query, the array will become 11 4 1 and 622. Then query of type 2 is given in which you need to return the sum of elements from second position to second position, means first index to first index. So what is the element at first index after query 1? 4. So you will return 4. Okay, so you will return 4. So in the answer array, the first element will be 4. Next, the query is of type 1 in which you have to update the values from first position to second position, means 0th index to first index. So I need to update these two values. So first has 2 digits, so it will be updated to 2, and 4 has 1 digit, so that will be updated to 1. So my array will become 2 1 1 6 22. The last query is of type 2 and you need to return sum of elements from position 1 to 4. So basically from 0 index to third index. So they are asking sum of elements of the complete array. So that is 626. So for queries of type 2, your answer will be 4 and 626. So this is what is asked in the question. Now let's see how we can solve it. Okay, so let's think about the solution of it. Okay, so what can be the brute force method? So brute force method can be for query of type 1, you run a loop from L to R and update the values. For query of type 2, you run a loop from L to R, add them to a variable sum and add that sum to an answer array. Okay, but that will take how much time? Each query will use a loop from N to R, so it will take big of Q of N time. This will be brute force approach, right? So we need to think of something more efficient. Okay, now for the efficient way, so let's discuss efficient way of query 1 and query 2 separately, how we can handle them. Okay, efficient way. Now, so for query of type 1 and for query of type 2. Now for query of type 1, we will discuss this afterwards. First let's discuss query of type 2. So for query of type 2, you need to return the sum of elements from L to R. So in this case, you can make use of segment tree, and in segment tree, you can store the range sum for the given array. Okay, and in big O of log n time, you can return the sum of elements from L to R. Now I am not going in depth of segment tree. What is segment tree? How do we build it? How do we query it? Because that will be a whole separate video. Right, so if you know segment tree, I will be using it here. Well and good. If you do not know segment tree, first go and watch segment tree video, learn it, and then come back here. Okay, so in segment tree, I'll do query operation, and that will return me sum of elements from L to R in big O of log n time. Okay, now let's come to the query of type 1. Now you see here, if in query of type 1, they would have asked to update us only one index I, then we could have used the update function of the segment tree, which updates a value in big O of log n time, right? But you need to update a range. So if you want to update a range, then for each query, if I update all the indexes, so one index, so it will be one index updation in segment tree takes log n time. So it will be q into log n into r minus l plus 1. And this r minus l plus 1 can be upper bounded by n, total number of elements. So this will be equal to big O of n into q into log n. So this will be even worse than the brute force approach. So we are not going to use it. So then how to update all the values from L to R? Now many of you might have thought here of using lazy propagation of segment tree, which can be used to update a range, right? Now there is a easier way for this question if you observe it a bit. Okay, so what is the easier way? See, every index which I update will not be updated more than thrice actually. So for every index, if I do update operation thrice, that can be at max 3 updation for every index. Okay, after that if you do update, the value will not change. How? I will let you know in a while. So if I do total even 3n number of operations for every index, if I do 3 number of updation, then also it will take me 3n log n totally for all the queries, right? Because for L to R, so basically what I mean is, let's say for in the first query you need to update some index I, so you updated it. In the second query you again need to update index I, so you updated it. In the third query you again need to update index I, so you updated it. Now if the ith index comes in any updation, you do not need to update it, because after at max 3 updation, the value of I value of that element will remain the same. How? Let's look at that. So basically how we will reduce the time. So instead of updating all the indexes from L to R, I will only update the index which are required. Okay, and any index will not be updated more than 3 times. Okay, so how? Let's look at it. So your array of I value can be either 1, or it can be from 2 to 9, or it can be from 10 to 10 ki power 9 minus 1, or it can be 10 ki power 9. Right, because in the question it is given that array of I is between 10 ki power 9 and 1. So if the value is 1, and if I update it, so it will remain 1 only, because the number of digits in 1 is 1, right? So this will require 0 updation. Okay, so why 0? Because now you cannot update it to a newer value, right? So even if 100 update operation comes for this index, even if I do not do any updation, then also it will work fine, because 1 will be converted to 1 only. For all the elements from 2 to 9, if I update them, they will be converted to 1, because all the elements from 2 to 9 have number of digits 1. Once they are converted to 1, if I again do update operation on this, they will keep getting converted to 1 only, because 1 has number of digits 1, right? So for these elements, I need only one update operation. After that, they will repeat the value 1. For the elements from 10 to 10 ki power 9 minus 1, what will be the number of digits? The number of digits for 10 to 10 ki power 9 minus 1 can be 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. Right, because the number can be, let's say, 15, so number of digits is 2. Number can be 222, number of digits is 3. Number can be 999, 886, number of digits is 6. So any value in this range will get converted to 2, 3, 4, 5, 6, 7, 8 or 9, depending upon the number of digits. Once they get converted to this, any of this value, if I do one more operation, they will be converted to 1, because 2 has number of digits 1, 3 has number of digits 1, 4 has number of digits 1, right? Basically after one update operation, this query gets converted into this. So after one more update operation, it gets converted to 1, because the number of digits are 1. Now if you keep on updating, it will get converted to 1 only. So for all the numbers which are in this range, it needs maximum 2 update operation, right? 10 ki power 9 has 10 number of digits, 1 followed by 9 zeros. See, so if you update it, it will get converted to 10. If you update it again, 10 has number of digits 2, so it will get converted to 2. If you update it again, it will get converted to 1, because 2 has number of digits 1. Now it will keep updating to 1 only. So how many operations are required here? At max 3 number of operations for 10 ki power 9, because after that 1 will remain 1 only. Okay. So now what I will do? So I will keep a track of the indexes whose value is not 1. Why? Because let's say, so I will keep a track of elements whose value is not equal to 1. The index of the elements whose value is not equal to 1, because I need to update only those elements. For example, if my given array is 1, 2, 3, 4, 3, 3, 3, 4, 1, 7, 9, 12 and 1, 3, 9, 6, 5, let's say. So these are the indexes 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now let's say I get a query of type 1 in which I need to update the elements from 5 to 7. First of all, I will keep the excess of the elements. I will store the elements store the index of elements whose value is not 1 in a sorted order. So this will give me 0, 1, 2, 4, 5, 6 and 7. So only these indexes can be updated. I cannot update this index because it will get again converted to 1. So why waste time? Now I need to update the elements from 5 to 7. So in the sorted list, I will do binary search and find the smallest index which is greater than or equal to L. Binary search and find smallest index greater than equal to L. And then keep moving forward until I reach the end of the array or I reach an index which is greater than R, because I need to update from L to R only, right? So I need to update from 5, 6 and 7. So if I do binary search, 5 is the smallest number greater than equal to 5. So I will update the fifth index. So fifth index is 9. So it will become what? It will become 1. Then sixth index is 12. So it will get converted to 2. And seventh index is 13965. So it will get converted to 5. Now from this list, I will remove those indexes who got converted to 1. So 5 index got converted to 1. So in further queries, even if I get 5 again, I do not need to update it. So I will remove 5 from this sorted list and it will become 0, 1, 2, 4, 6 and 7. Now if a query of type 1 comes where I need to update the elements from second index to fifth index. So here I have, if I do binary search, I will come on second index, then I'll go to fourth index, then 6 is greater than 5. So I will update these two elements. So second index is 4, it will get converted to 1. Now you see we skipped the third index and fifth index, right? So this will save over time. Then fourth index. So fourth index is 7. It will also get converted to 1. So both these get converted to 1. So I will remove 2 and 4 from the sorted list because now further they will not be updated. So 0, 1, 6, 7 and so on. So in this way, each index will be updated at max 3 times. Even if it is 10 to the power 9, it will be updated 3 times. After that, it will not be updated. We will remove it from this sorted list. Okay. And how we will update it? So we will update it in the array index also. So array of I will also be updated, and this updation we also need to reflect in the segment tree using the update operation. Okay, so how does the update operation work? What is the segment tree? How we store the range of sum in the segment tree? What is the build query? I am not going to discuss that, assuming segment tree you know or you learn before moving into the solution. Okay, so this is how we will solve it. So if a query of type 2 comes, directly use query function of segment tree, return the sum. If query of type 1 comes, then from L to R you need to update the values. So first do a binary search in the list of indexes where the values are not 1 and find the smallest index which is greater than equal to L. From there, keep moving forwards up till either you reach the end of the list or you reach a value greater than R, and for all the indexes, update those indexes with number of digits. And if number of digits becomes equal to 1 at a certain index, then remove that index from the list so that you do not update it in the further rounds. Okay, so let's look at its implementation. So this is the function range sum digits which I need to complete. I have given n the number of elements, vector array, q is the number of queries, and this queries is the 2D array in which queries description is given. So this is my final vector answer. So this is my answer vector which I have named final. Then this is tmx is my segment tree. Okay, so I have here a return vector long tmx in the public area, and for segment tree you need to go till 4n. Okay, but I have taken 4n plus 50 and I have pushed all the values as 0 by default. Then I have passed the build function which will basically build the segment tree with respect to the initial array. Okay, so this is the build function. I am not going into depth of that. Then I have taken one set. Now I need to maintain a sorted list of elements of indexes whose value are not equal to 1, and I also need to efficiently remove the indexes from that. So the best way to do is using set. So inserting an element will take log n time, removing an element will take log n time, and querying an element will also take log n time, right? So first of all, for I equals to 0 to n minus 1, for all those values which are not equal to 1, I will insert their indexes in the set. Now I will traverse through all the queries and operate them. So int type is equal to queries of I0. int L is equal to queries of I1 minus 1 and R is queries of I2 minus 1. Why are we doing minus 1 here? Because in the question they have given with respect to 1 based index, or you can say they have given position, but our original array is 0 based index, so I have to do minus 1. If the query is of type 1, then do this. If the query else, just do query operation on the segment tree from L to R, and it will return you the sum of elements from L to R in the log n time, and push that value in the final vector. Okay, so this is the query operation. You can have a look at it. And if the query is of type 1, then first of all I will check if the list is empty, so I cannot update any index, so I'll simply continue to the next query. Otherwise I will do s, that is the set dot lower bound L. So what this will do is it will return me an iterator to the value which in the set s, which is just greater than equal to L. So if it will find exact value L, it will return me iterator to that. Otherwise it will return me iterator to the next element which is greater than L. Okay, then I have taken one vector temp. So in temp vector I will store the indexes of all the elements who after getting updated got converted to 1, because I need to remove them from the set later on. Okay, so to keep a memory of that. Now now I have got a iterator to the lower bound of L. Now I will keep moving over the iterator. I will keep doing iterator plus plus until I reach the end of the array, or until I reach the end of the set, or I reach an index which is greater than R, right? So while iterator is not equal to s dot end, it is not the end of the set. Get the value at pointed by this iterator. So you get it using star iterator, store it in the index. If index is greater than R, then break, because you have reached the value greater than R and you need to update from L to R only. Otherwise, so new value which will be updated to array of I will be the number of digits in it. So I have called this function karo in and passed the element array of index. So this will basically count the number of digits in n, okay, in the array of index element. So it will say count equal to 0, and while n is greater than 0, count plus plus and n divide by 10 and return count of elements. Okay. Then once you get the count of elements, so that will be the new value which you need to update. So you will update it in the segment tree using this function. You will update it at this index, and if the new value is 1, so if the updated value is 1, you need to remove this index from the set. So you keep a memory of that in the temporary vector and then move to the next iterator using iterator plus plus. So this process continues until index becomes greater than R, or you reach to the end of the set. Okay, this is the update function for the segment tree. Okay, and after you finish doing the updation from L to R, for all the elements which are stored in the temporary array, you remove it from the set. So you say s dot erase temporary of J. Okay, so in this way you'll process with queries of type 1 and type 2, and finally return the final answer. Okay, so queries of for all the q queries, you do your log n for the binary search, and at max there can be how many operations? There can be n 3n number of operations, so that will be 3n log n, right? So overall you will solve it much more efficiently and solve within the time limits, and finally return the answer vector. Okay, I hope you have understood this complete solution. Thank you.